Okay, friends, let's get you some solutions to this second randomness homework. We got experiment number 4, which is a replication of experiment number 2. I got it open down here. Here she is. So we're gonna deal out cards until we get all the suits. So here you see in this one I just opened up, it took 7 because it went clubs, hearts, hearts, diamonds, and then finally spades. Let's do it again and see what happens. That one took 6. Spades, diamonds, clubs, diamonds, hearts. That one took 5. That one took 4. There you go, one of each. I'm going to hold this down and let it run a little bit and kind of talk while we're doing this. You notice that some of those go pretty long. I mean, and one of the questions I'll actually answer while I'm generating data. I'll answer question number 3 first. It says, you may have noticed that the number of cards dealt column goes out to 40. Why 40? Why is 40 the greatest number of cards that you'd have to analyze? And the answer is pretty straightforward, but it might not be obvious because if you've dealt out 39 cards, there's no way the 40th one can't be the last suit. Think about why. If you think about the suits in a deck, there are 4 of them, spades, clubs, hearts, diamonds. Worst case scenario, you can deal out all 13 of one, 13 of another, and 13 of a third, and then you've got 13 cards left that are all the same suit. So as unlikely as it is, for example, as we've run this experiment, the biggest number I've got was 25. 40 is the most, and I've never actually witnessed it hit 40 while doing this experiment, either in class with kids and cards or running it as a simulator here in Excel. But there you go. So the first thing we want to do is we want to figure out on average how many cards it takes. So I'm going to do this just like we did in the videos. We're going to do the number of cards times how many times we saw that. I'm going to copy that down, and every time I do this, you'll notice this is updating over here because that's the way Excel works. I'm going to copy this over and make it a sum. There we go, and then I'm going to equals, and I'm just going to divide how many cards have been dealt by how many trials we've done, and it looks like about 7.6 cards, and it's not really changing all that much at this point. 7.61, 7.60, 7.62. It's about 7.6 cards. And there you go. That's pretty much all you had to do for the first part. Oh no, I had to make a bar graph too. I'll make a bar graph. Sure, why not? So here's your frequency. So I'm going to graph the frequencies as a column chart. And then the only problem with this is, well, I'm actually going to make them wider. I don't like it when they're that skinny. This is just me being me. Our gap width. There we go. There we go. It's a little bit. Let's bring it all the way over. There we go. And then we're going to make, sorry, I'm going to geek out a little bit here and make it look pretty. We're going to make the line be black so it stands out. Maybe bring the width up a little bit. It looks a little bit sharper. You know what I'm going to do? I'm going to add the data labels and I'm going to delete the axis because that, I kind of like that better. Yeah, I like the way that looks better to me. It's easier than trying to bring the bar over to the vertical axis. The only thing I want to do is give it a title and a horizontal axis. Oh, and there's one more thing I want to do too. So let's give it a title. This is experiment number 4, number of cards until all suits, or something like that. You can give it whatever. Maybe you want to spell experiment correctly, Sean. There we go. We want to give it definitely a horizontal axis. Axis titles, primary, horizontal. This is number of cards. And cards has an A in it, I believe. Yes. And this is a problem. It goes from 1 to 37, and it should go from 4 to 40. So the easiest way I've found to get around this is just right-click on the graph, select data, and where it says horizontal axis labels, edit that and select the ones you want. I've never found an easier way of doing it than that. That's, to me, the most straightforward way. There you go. That's a pretty graph. You can pull it down if you want. And what's cool about this is, too, you can keep the experiment running. And the graph will just keep updating as you go, which is pretty slick if you think about it. Okay, so there's the first 3 questions. Let's get back in here. Now let's use that graph of yours and analyze deeper. In number 1, you rounded off your average to the nearest whole number. Oh, I forgot to do that, actually. So that would be 8. Assuming it's still 7.6. Yeah, so going to round that off to 8. All right. Let's see what we got. Equal, oh, what percent of the data are equal to that average? Okay, well, here's where we got it. It's not, this is old math, but it might throw you for a loop. So there's your average right there. I'm going to highlight this whole row right here. Okay, that's your average, 8. 293 of the experiments were equal to 8. So to know what the fraction or percent of the experiments would be, I'm going to call this column percent. You just go that divided by that. And I get about 12%. Roughly 12% are exactly equal to, oh, why? I thought I changed it to a percentage. Oh, there we go. Are exactly equal to 8. And you can let it run, and it's not going to change all that much because we've begun to stabilize now. Now, you might wonder why I changed the D42 to an absolute reference. That's the total down here. That's because I'm going to drag the formula now down. Whoops. Excuse me. Undo. I'm going to drag the formula down, and I'm also going to drag it up, and I'm going to do the percentages for everything. So 10% took 4 cards, 16% took 5, 16% took 6, 15% took 7, and it's pretty stable at this point. It really isn't changing all that much. It will change a little bit as data is added. The sum total of all of these, of course, is 100%. And you're going to get these things eventually will have things in them as well. But for right now, it's definitely stabilized for the most part. So the next question is, what percent are less than 8? Well, that's 7, 6, 5, and 4, which would be these 4 percentages right here, which looks to be 57% or 58%, depending on which you round off to, 58%. This is 11% now. It's not 12 anymore. Now it's 11, which means these are whatever's left, 31% or so. So that's what's going on here. Boom, boom, boom. The extra credit's kind of fun. In these videos, we explored how to calculate the average. And the first question was, why do we do an average? And there is no good answer to that. I just wanted to see what a lot of you said. Most of you kind of didn't try that one, which is okay. I have a theory as to why we do it that way. I'd be happy to share it with you if you want to hear it. And quite a few of you actually got when you shouldn't use averages. And averages shouldn't be used when you have highly skewed data values. Like, for example, you might have noticed that these data values kind of make a bit of a hump, but 8 is off the hump. We're getting into a little bit of Math 243 land here. It's pretty funny. Donna just sent me an email. She's actually the Math 243 instructor. She would enjoy this conversation. If the skew gets too great, you want to stop using averages and maybe start using things called medians. But I'm not going to get too far into that. This homework isn't intended to get you into that. It's mostly just to show you how to deal with grouped data. And I think we did a pretty good job there, so I think I'll stop. See you in class.